For 69 years, a transport aircraft rested partially submerged in the frozen marsh of the Taymyr Peninsula. The object was a military transport airframe trapped in suspended degradation inside Siberian permafrost. The operation to document and retrieve this machine would require navigating a severe logistical lock. The aircraft is a Douglas C-47 Skytrain. It rolled off a United States assembly line in February 1943. Engineered as a rugged cargo and passenger military transport, the metal structure was transferred to the Soviet Union under the Lend-Lease program. After transfer through the Soviet wartime aviation system, the transport later moved into polar and civil aviation service and received the registration USSR-L1204. The aircraft carried the structural architecture of an American transport, yet it operated deep within the Soviet logistical network. This dual identity reflects the complex supply lines required to move cargo across vast distances. The airframe was built with conventional 1940s aluminum alloy and designed to handle the stress of unimproved forward operating bases. The final resting place of this transport is a featureless tundra marsh on the Taymyr Peninsula. The procedural reality of this site is defined by its extreme lack of access. There are no roads. There is no infrastructure capable of supporting heavy overland extraction equipment. The permafrost operates as a natural vault that changes state with the seasons. During the brief summer window, the upper layer of the soil thaws into a saturated marsh. The heavy point loads of the aircraft, particularly the engines and the main landing gear structures, sink into the softened ground. When the Arctic winter returns, the ground refreezes solid. This annual cycle locks the aluminum airframe firmly into the ice. This freeze and thaw pattern repeated itself for nearly 7 decades, likely helping hold the C-47 in the Siberian landscape, rather than preserving it as a clean, dry relic. The recovery objective for this site is highly specific. The goal is to salvage the intact 1943 airframe from the isolated tundra for museum restoration. Standard recovery cranes and flatbed trucks could not reach the site. The marsh prohibited heavy overland movement, leaving airlift as the only practical vector in or out. The aircraft must ultimately be extracted without inducing structural failure during a lifting process. The physical condition of the aircraft after 69 years dictates the entire procedural approach. The site is not a scattered debris field resulting from a high-speed impact. It is a coherent structure sitting flat on the terrain. The intact nature of the fuselage creates a specific operational paradox known as a thermal shelter trade-off. When an aircraft comes down in a lethal Arctic environment, the intact aluminum tube immediately serves as a primary survival asset. The metal skin successfully blocks the driving wind and provides a sealed volume against extreme external temperature drops. It functions as an excellent static shelter. However, an immobile shelter in an uninhabited zone creates a rigid procedural trap. Remaining inside the sealed structure protects against immediate environmental exposure, but doing so guarantees eventual starvation when there is no external communication network to trigger a localized rescue search. The physical asset that keeps occupants alive in the short term becomes a static anchor that prevents self-rescue. The occupants must decide whether to abandon their only protection from the wind to seek a communication vector, or remain in the shelter and wait for a search grid that may never reach them. The same intact fuselage also preserved the crash evidence. Instead of fragmenting into a debris field, the airframe points to a controlled descent with minimal forward velocity and a flat attitude. What precise technical failure forced the aircraft down into this frozen isolation? On April 22, 1947, an operational time window dictated the survival of everyone on board, though later sources disagree on the exact passenger count. The transport aircraft departed before the crew encountered a serious mechanical fault. The left engine developed oil pressure and temperature trouble and was shut down. This forced the aircraft from normal twin-engine flight into a prolonged single-engine emergency. The remaining flight path was entirely governed by the thermal and mechanical limits of the single operating power plant. The crew had to extract exactly enough thrust from the right engine to maintain altitude without immediately destroying the engine itself. Flying a loaded transport on asymmetrical thrust creates a severe operational constraint. The loss of the left engine induces a massive yawing force that the pilot must counter with continuous physical rudder input. The pilot must maintain a minimum control speed to prevent the aircraft from rolling out of control, while simultaneously carrying the aerodynamic drag of the dead engine. This requires high throttle settings on the functioning right side. The decision matrix is binary: reduce power and lose altitude, or maintain power and risk thermal destruction. Operating a loaded C-47 on a single engine can force the remaining power plant into a narrow margin of temperature, oil pressure, and power management. The crew had to balance altitude against the rising stress on the second engine. After several hours, that remaining engine also overheated and failed. With both engines no longer producing usable power, the aircraft became a heavy glider over the Siberian landscape. Losing all thrust over a featureless frozen marsh imposes an irreversible constraint boundary. There is no thrust available to alter the descent vector. There is no possibility of a go-around. The descent profile must be managed perfectly on the first and only attempt. Commander Maxim Tyurikov had to select a viable impact zone and establish a steady glide path while the heavy airframe rapidly lost altitude. The terrain below was not flat. The frozen tundra consists of hard ice ridges, uneven depressions, and solid permafrost hummocks. The physical dimensions of the transport aircraft, with its wide wingspan and long fuselage, made it highly vulnerable to off-axis deceleration. The crew had to systematically bleed off airspeed while navigating these ground hazards. Tyurikov had to execute a forced landing into the tundra and snow with almost no remaining energy margin. Russian accounts describe the aircraft coming down into a swampy tundra surface, where the landing tore away the left engine and heavily damaged the forward nose section. The survival problem was not a clean gear-up slide along a prepared surface. It was a controlled emergency arrival into deep, uneven Arctic terrain, with enough discipline to keep the cabin from breaking apart. The cabin remained survivable, the fuselage stayed largely coherent, and no one was killed in the landing itself. All 32 individuals on board survived the immediate crash sequence. The machine came to a complete halt, embedded slightly in the uneven ice. With flight over and rescue uncertain, the crew had to record what had happened before deciding whether anyone could cross the tundra. A forensic assessment of an isolated airframe often yields conflicting visual markers. The exterior empennage of the stranded transport displayed a painted United States military serial number. Inside the sealed cabin, the primary chronological evidence consisted of a handwritten Cyrillic timeline. These two distinct data points establish the operational identity and the exact sequence of events without relying on external assumptions. Following the forced landing, the immediate priority shifted from flight control to documentation and survival strategy. Without automated flight data recorders, Tyurikov and the passengers left written evidence directly on the aircraft's inner skin. The surviving notes were made with a chemical pencil, not a modern recorder or a formal accident log. They preserved the takeoff time as 0030 and the landing time as 0530, turning the cabin wall into a stark human record of the flight. 4 days after the landing, Tyurikov left with the flight mechanic, the radio operator, and 6 passengers to seek a settlement or a nomadic camp. They never returned. Tyurikov's remains were found in 1953. The other 2 crew members and 6 passengers are still recorded as missing. The remaining occupants stayed inside the fuselage for 19 days. A search team finally located the intact structure, and the survivors were rescued on May 11, 1947. After the personnel were extracted, the empty airframe was left exactly where it had stopped sliding. At this point, the aircraft entered a long period of environmental slowdown rather than perfect stasis. The cold tundra climate sharply reduced many forms of chemical activity, helping paint, metal, and cabin markings survive far longer than they would in a warm, wet storage yard. But aluminum corrosion does not stop completely. Moisture, salts, soil, and contact between dissimilar metals can still create local damage, especially where water is trapped in joints and lower compartments. The tundra preserved the aircraft unevenly. It protected some evidence while locking other parts into mud, ice, and swamp water. That uneven preservation left the exterior markings legible long after the machine's operational life ended. The original U.S. Army Air Forces serial 42-32892 remained visible on the tail structure. This physical evidence stood beside its later Soviet registration and gave curators a direct way to identify the airframe. Matching the painted serial to historical manufacture and transfer records, then comparing it with the cabin writings, locks the identity of the machine without relying only on secondary retellings. The verified historical value did not solve the extraction problem. The machine remains firmly embedded in a marsh completely cut off from heavy overland access routes. To reclaim this forensic artifact for an urban restoration facility, it must be removed through the air. The structure was never designed to be lifted by a single external cable. How can a salvage team safely dismantle a preserved but fragile airframe stranded miles from any road? In August 2016, a 15-person expedition organized through the Russian Geographical Society entered the Taymyr site to solve the artifact problem, not merely the transport problem. Their mandate was to reclaim a rare Lend-Lease aircraft for museum restoration, so dragging the 73-year-old aluminum frame across uneven tundra would have destroyed much of the historical value the cold had preserved. The operation, therefore, had to be built around field disassembly and aerial extraction. The physical size and total weight of a fully assembled Douglas transport exceeded the external lifting capacity of the designated extraction helicopter. To stay within payload limits without turning the aircraft into scrap, the team had to dismantle it on site along structural joints that could later be read and reassembled. Skins, frames, spars, fasteners, bolts, and attachment points had to be preserved wherever possible. The goal was not to open a pressure hull, but to keep the C-47's historical structure legible for restoration. Working on the Taymyr Tundra in August introduced a severe local constraint. The upper layer of permafrost had thawed into saturated marsh, so the 15-member team had to execute heavy mechanical separation while standing in freezing mud and preventing massive components from shifting or collapsing into the water. Across roughly a week in the field, 5 continuous days were consumed by mapping load paths and executing the disassembly plan. The technicians systematically isolated the major structural zones of the transport: the fuselage, the center section, the engines, and the wings. By the end of the 2016 operation, the expedition had converted one massive, immovable object into recoverable modules and moved the main aircraft sections toward Krasnoyarsk. The work was not finished in a single clean sequence. The wings were evacuated a year later. However, isolating the modules on the Marsh was only the first half of the mechanical puzzle. The extraction phase required moving these awkward, fragile shapes from the surface into a dynamic flight environment. With the joints severed, how does the team physically lift the sections into the air without inducing structural collapse? The wreck lay about 180 kilometers from Volochenka, but the extraction geometry was governed by a shorter and more practical route to water transport. From the forced landing site to the Pyasino River was about 78 kilometers. No ground vehicle could simply bridge that marsh, so the logistical puzzle shifted from ground disassembly to helicopter lift and river transfer. The operation utilized an Mi-8 transport helicopter, which imposed a strict sling load limit on every recovered module. If any component exceeded the external cargo hook capacity or carried too much trapped water from the marsh, safe vertical lift would fail and the extraction would have to stop. The field cuts had therefore been engineered around helicopter payload margins before any rigging began. The answer was rigid load path discipline. The separated fuselage is an empty, 69-year-old aluminum cylinder. Attaching standard lifting cables directly around its circumference would instantly crush the thin structural frames the moment the helicopter applies vertical tension. To prevent a catastrophic crush, the ground rigging crew had to calculate the exact center of gravity for each irregular module. They distributed the lifting forces across specialized wide straps, passing the loads entirely through the reinforced factory bulkheads rather than the fragile outer skin. Once the rigging is locked, the helicopter must slowly build tension to break the suction grip of the frozen mud. When the module breaks free, the cargo's aerodynamics become the primary operational hazard. The suspended section generates massive drag. It acts as a blunt airfoil suspended under the rotor wash. The helicopter pilot must execute a highly controlled low-speed flight profile to prevent the heavy aluminum tube from oscillating wildly. A swinging load of that volume will pull the helicopter out of controlled flight or force the pilot to jettison the artifact entirely to save the aircraft. The team did not need to fly the full 180 kilometers to a settlement. The practical solution was to transfer each section from helicopter lift to river barge. This created a precise intermodal chain. Tundra disassembly, Mi-8T sling lift, river loading, and onward movement by water. Moving fragile aluminum sections from the dynamic stress of a helicopter sling directly onto the flat deck of a river barge represents a severe handling challenge. The helicopter must transition from forward flight to a perfectly stable hover over the moving water. The pilot then slowly lowers the swinging aluminum frame toward the rigid steel deck. The surface of the barge provides zero shock absorption. The receiving crew must physically guide the suspended load into custom-built cradles before the sling tension is completely released. Dropping the load even a few inches onto the steel deck could buckle the lower longerons, instantly undoing the careful work of the Tundra disassembly. The transition from vertical tension to gravity resting on the cradles must be flawless. The Mi-8T completed 5 flight cycles in the 2016 operation, carrying major sections from the Tundra to the river loading point. That extracted the principal aircraft structure from the permafrost trap, but the operation as a whole remained staged. The wings were evacuated in 2017. The barge then began the slow river journey through the northern waterway system, moving the dismantled aircraft toward Dudinka and then Krasnoyarsk. The intermodal transfer succeeded because the aircraft was treated not as cargo scrap, but as a fragile museum object in transit. However, extracting the aircraft from the frozen marsh initiated an entirely new chemical threat. How is a structurally stressed aluminum artifact secured against immediate atmospheric degradation after leaving the deep freeze? The physical extraction from the Taymyr tundra solved the primary logistical problem, but it immediately triggered a chemical trade-off. The permafrost had operated as a thermal vault. Once the transport was lifted from the frozen marsh and moved south, the heavy aluminum frames, thin outer skin, and internal bulkheads met warmer air, higher humidity, and oxygen. If the recovered sections were placed in a standard outdoor storage yard, moisture and oxygen could accelerate galvanic corrosion, blister original paint, widen microscopic cracks, and threaten the exterior tail numbers and interior flight log within a few seasons. To neutralize this threat, the dismantled sections moved from extraction into a controlled conservation chain. In December 2021, the C-47DL USSR-L1204 was transported from Krasnoyarsk to Novosibirsk for restoration in a special hangar at Moshish Airfield. That move marked the shift from recovery logistics to long-term restoration and conservation. The immediate requirement was assessment and cleaning. Mud, swamp water, damaged skin panels, and deformed structural parts all had to be dealt with before the aircraft could be rebuilt as a museum exhibit. Cleaning then became a controlled conservation step, not a cosmetic wash. Abrasive methods could damage paint layers, surface traces, or cabin writings. So restoration reports describe careful examination, cleaning, straightening of damaged lower fuselage skin, restoration of cabin equipment, and work on the engines, tail, center section, and interior. Broader conservation logic still applies. Metal artifacts need controlled humidity, clean storage, and careful treatment after long exposure to mud and water. The specific chemicals and coatings used on this aircraft should not be stated unless the restoration team documents them. Every recovered structural zone is examined and mapped for museum restoration. The engineering logic that guided the Tundra disassembly now guides the reassembly, but the objective is historical appearance and interpretive display, not a return to flight status. Restorers can rebuild the central structure, wings, engines, cockpit, and cargo cabin as a coherent exhibit, preserving original and non-recoverable parts where appropriate rather than pretending the aircraft has regained full operational strength. The stabilized airframe's final destination is a curated public display that reads as a physical record of cold-weather aviation logistics. With the visual evidence intact, visitors and researchers can read the machine's American construction alongside its Soviet operational life. The transition from an isolated tundra wreck to a curated museum artifact required navigating multiple sequential failure points. The aircraft survived the initial thermal failure of its remaining engine. It survived the geometric hazards of a gear up landing on uneven ice. It endured nearly 7 decades locked in a freeze and thaw cycle. Finally, it survived an extraction operation bounded by strict aerodynamic weight limits and immediate chemical threats. Together, those stages show that historical evidence can survive only when each constraint is answered in sequence.